A groundbreaking discovery has been made by astronomers, revealing the most distant black hole ever observed in X-rays. This remarkable finding was made possible through the utilization of the James Webb Space Telescope. What makes this black hole particularly intriguing is its early developmental stage, a phase never before witnessed, where its mass is comparable to that of the galaxy it resides in. This discovery holds immense significance as it sheds light on the formation process of some of the earliest supermassive black holes in the universe. To know more, stick with us till the end of this video and subscribe to our channel for more intriguing and thought-provoking content on space science. The way galaxies form, how black holes grow, and the appearance of quasars shake up what we know about how the universe evolves. The quick expansion of supermassive black holes in the early universe suggests that how they form and grow might be different from what we thought. This discovery sparks new paths for research and raises interesting questions about how supermassive black holes grow and their connection with the galaxies they're in. Isn't it amazing to think about the discovery of UHZ-1 and learning about what it is? It's incredible how telescopes like the James Webb Space Telescope, JWST, and Chandra can reveal such far-off and mysterious things in the universe. UHZ-1 being labeled as the first ultra-distant galaxy, along with its link to a quasar, offers us precious glimpses into the early universe and how supermassive black holes evolved. Quasars, fueled by these colossal black holes, rank among the universe's most energetic entities. Finding one at such an immense distance sheds light on the universe's state during its earliest stages. Discoveries like UHZ-1 expand the horizons of our understanding and ignite a deeper curiosity to explore the cosmos. There are two main theories about how black holes grew in the past. One suggests they began small and grew rapidly, while the other proposes they started out much larger than the ones we see forming from dying stars today. These theories are known as the small seed and heavy seed models. By studying UHZ-1, we can gain insights into which theory holds true. Let's explore the small seed model. Can a tiny black hole become a mighty quasar in less than 1 billion years? It's a puzzling question. Black holes feast on gas, but there's a speed limit to how much they can gulp down, no matter how hungry they are. As gas swirls into a black hole, it heats up and glows, pushing against more gas trying to come in, like a cosmic tug of war. Bigger black holes can feast more and shine brighter, but there's a line they can't cross, called the Eddington limit. Even if a black hole feasts at its fastest for 1 billion years, it still wouldn't bulk up enough to explain those early quasars. But don't worry, there are ways to solve this puzzle. Some experts suggest that black holes can gulp down gas faster than this limit, but it's a tough task. They'd need to feast non-stop. Another idea is that many black holes could band together quickly, or we could start with gigantic stars that leave behind black holes hundreds to thousands of times bigger than today's stars. In our modern universe, exploding stars scatter heavy stuff, shaping gas clouds into smaller stars. But in the early days, the cosmos was pure hydrogen and helium, likely birthing gigantic stars and hefty, though not super hefty, black holes. With a speedy, steady feast and hefty stellar seeds, we could see supermassive black holes emerge in less than 1 billion years. But there's a problem. Why don't we spot any black holes between 100 and 100,000 times the size of our Sun? If supermassive black holes grew from smaller ones, we'd expect to find some in this range, but they're nowhere to be seen. Now, let's talk about the heavy seed model. What if supermassive black holes didn't come from the dense cores of dead stars? It's time to debunk a myth. Making a black hole doesn't need super dense stuff. Any chunk of matter can become a black hole if squeezed into a tiny space called the Schwarzschild radius. Imagine this. For the Sun, that space is about 3 kilometers, squishing a solar mass into a tiny cube denser than a mountain. But picture a typical supermassive black hole. With 1 billion times the Sun's mass, it has a Schwarzschild radius as wide as Neptune's orbit. 1 billion suns crammed into that space would be as fluffy as cotton candy. Yes, you heard that right. Packing a solar system with cotton candy could birth a colossal black hole. The early universe may not have had cotton candy, but it was brimming with gas that would eventually give birth to stars and galaxies. In the early days of the universe, some dense clouds of gas might have skipped the step of forming stars and directly transformed into black holes. This was possible because the gas back then, mainly hydrogen and helium, didn't easily break apart during collapse. Theoretical calculations suggest these black holes, known as direct collapse black holes, could be about 100,000 times the mass of our Sun. Supermassive black holes, SMBHs, are incredibly massive objects with strong gravitational pull. Traditionally, it was thought they formed from small seeds, possibly remnants of massive stars collapsing under their own weight. These seeds were believed to gather mass slowly over billions of years, feeding on surrounding matter and growing into the massive black holes we see at the centers of galaxies. However, recent discoveries, like the observation of UHZ-1, have cast doubt on this idea, suggesting a possible shift from the traditional view of how SMBHs form. UHZ-1, a quasar spotted just 500 million years after the Big Bang, presents a significant challenge to the standard understanding of SMBH growth. Unlike previous distant quasars, such as J1342+0928 and J0313-1806, which emerged around 700 million years after the Big Bang and were remarkably large, UHZ-1 disrupts the expected timeline. Its appearance much earlier than expected, by approximately 200 million years, raises serious questions about the idea of SMBHs evolving from small seeds within such a short period. Insights from the James Webb Space Telescope, JWST, shed more light on the distinctive traits of UHZ-1. By capturing images that unveil intense quasar emissions and about 40 million times the mass of our Sun in surrounding stars, the data hint at a difference between UHZ-1 and the usual way supermassive black holes form. This difference supports the heavy seed model, proposing that supermassive black holes might emerge directly from massive gas clouds, skipping intermediate stages of star formation. The impact of UHZ-1 stretches beyond just astrophysical theories, influencing how we perceive the evolution of galaxies and the formation of cosmic structures. Typically, galaxies are thought to evolve in tandem with their central black holes, with the number of stars in a galaxy linked to the size of its central black hole. However, UHZ-1's distinct features challenge this idea, suggesting a separation between the mechanisms driving black hole and galaxy growth. This could lead to a new category of galaxies known as overly massive black hole galaxies, OBGs. What do you think will be the origin of these supermassive black hole? Let us know in the comments down below. If you found our video informative, then don't forget to hit the like button, share with people having the same interest as you in space science, and subscribe to our channel to never miss an update from us.